Okay, welcome back everybody to the second of a double header lecture after my microphone snafu yesterday. I checked the recording for the other half. It does look good. So I'm guessing I just screwed up my microphone yesterday, and that is totally my fault. I apologize about that. What we need to talk about in the second half of today's lecture / instruction is annuities. This was supposed to be what I talked about today anyway, so we are right on track still. We're not behind. An annuity is a compound interest situation, but with a little bit of extra. And that extra bit is going to be more complicated because we are putting money into the accounts, or something is putting money into the accounts. So it's growing with compound interest, but it's growing with a little bit of help too, right? And so we're going to have to keep track of that growth a little bit separately at first, because we're going to be doing it in a table, just like we did it in a table with compound interest. But then we're going to see there's a formula to help us out quite a bit with that. And so an ordinary annuity, I had to put ordinary in parentheses because there's many kinds of annuities, but for all the formulas that you look up online, they're going to be ordinary annuity formulas. Anybody, unless you're like in accounting, is going to use the ordinary annuity formulas. Of course, if you are an accounting major, please forgive me for the butchering that I'm about to do to the wonderful formulas of accounting. We'll use it for a very specific reason in this class. An ordinary annuity is a stream of payments. I'm going to underline that because I want to emphasize that unlike the previous scenarios, right, this is a stream of payments, right? So I can't talk about a single present value, right, because that present value is going to be worth different amounts. It's going to be a different value every time we add a little bit more money to the account. Well, the present value is going to change, right? So that's why we can't use the previous formulas. But it's a stream of payments made at the end of every time period, right? That's important. The ordinary annuities make it at the end of the time period. So when I deposit money into the account, right, it won't have enough time to grow, right? I have to wait for an entire month before it actually starts growing, because you can think about this as me putting the money in the bank on the 31st. There's not enough time for it to grow. Deposit into an account which may earn compound interest. Right? So simple interest became compound interest. We saw the rolling snowball interest on interest effect before. Now compound interest is going to grow into annuities, and that's us adding a little bit more. Right? We see these all the time, right? If you have a savings account and you're saving up to buy a new car, and you're saving away maybe $50 a month, right? That's an ordinary annuity, which you have created for yourself. I'm stashing away that money. If you are somebody who is retired, right, they probably have some kind of annuity, right? They earn a little bit of money every month, right? Social Security works as an annuity, right? It is a stream of payments paid to you at the end of every time period. Right? Now, you probably don't put all that money in a savings account and just leave it there, right? But it could work that way, right? Structured settlements, like if I were to win a lawsuit, right, and be awarded a certain amount of money every month, right, that could work as an annuity, right? When I pay money on my mortgage, that's an annuity, but it's not an annuity for me. That's an annuity for the bank, right? The bank has already paid the money for the house. It's their house. I'm just paying the bank back, right? So I'm paying the bank a payment every month. Same thing when you buy a car. And when you buy a car, right, the bank has already paid the money for you when you bought the car. The dealership gets their money right away. They get 100% right away. And it's just you're paying the bank back with interest, of course. That's why the bank is willing to do that. But for the bank, that's an annuity. And so we see these annuity formulas a lot. We'll see them both in savings and in loan contexts. I'm going to use the present value, future value terminology when I talk about annuities, right? Not the A and the P that I did before when I talked about compound interest and simple interest. Our formulas there had A's and P's, but with ordinary annuities, I'm going to talk with present value and future value terminology. Most of the formulas that you see online will do the same thing: present value, future value. Right? So the interest earned per period will be I, just like it was in the compound interest formula. The total number of periods is N, just like it was in the compound interest formula. And I'm going to add one more variable to the end here because I forgot one when I was half writing this before I started recording. Is PMT. That's the payment per period. That's how much extra I put into the account every period. Or if we're talking about a loan, that's how much you're paying the bank every period. Think of that as your loan payment every period. So PMT, I know it's weird to have variables with more than one letter, right? PV and FV might not be a stretch for you, but PMT, that's one variable for us. And rather than come up with a brand new letter, right, we just call it PMT. That's the payment for every period. Now, to make this easier, right, what we're going to do is we're going to make the compounding frequency, which remember, compounding frequency in compound interest terms was how often we recalculated the interest. We're going to make the compound frequency the payment frequency, that is, how often we actually put a new payment in the account, and the length of the periods, we're going to force them to always be the same in the annuity formulas. Right? That doesn't mean that we can't stretch our brains a little bit and make them different, but I don't want to give you an annuity situation that compounds every quarter, but we pay into it twice a month, and we're going to recalculate the interest every month. Right? It's not useful. Right? We can usually manipulate it so that they all line up. Like, for example, if we made 2 payments every month, I would just group them together and say that's the same thing as 1 payment at the end of the month. And we can't really fix the compounding frequency and period length, though. So I will always force them to be exactly the same when I'm doing the annuity formulas, right? It would be much more complicated if they weren't the same. Right? So in the book, in the homework, in the test, those things will always be exactly the same, just to make our lives a little bit easier. But it's a stream of payments. Right? So to analyze a stream of payments, we're going to have to get a little bit creative. And here's my first example. Right? Let's take an annuity that pays $1,000 per year over the course of 3 years. And we're going to earn 4% APR compounded annually. Here we see the first time where the time periods has to match up, right? Years, years, years. All of those time periods have to match per year. And I'd like to talk about the future value of that annuity. Now, I know too much you might be thinking, Professor, I can do that. $1,000 per year times 3 years. That's $3,000 at the end of 3 years. And you'd be right. That would be what I call the nominal value of this annuity at the end of 3 years. That's just sort of the face value. The total amount which has been placed into this account is $3,000. But remember, each time we put money into the bank, it's going to start earning interest. So not only is this $3,000 going to earn a little bit of interest, but we're going to have some of that interest on interest effect. So let's see. So we know that there's a $3,000 basis on this annuity. That is, the amount of money that we've actually put into the account is $3,000. Well, let's see how much more than that we'll earn from the growing, from the annuity-ness of it. I put $1,000 in the bank every year at the end of the year. $1,000 at the end of year 1, $1,000 at the end of year 2, and $1,000 at the end of year 3. And there you can see the $3,000 basis, right? Before any interest gets applied here. Well, again, that's just you can think of that like the present value part of it. Let's let this money grow. And I'm going to have to keep track of every payment separately, at least in the table. So how long does this payment stay in the bank? Remember, it went into the bank at the end of year 1. Right? So it's not growing any during year 1 because it only happened on December 31st. But for all of year 2 and all of year 3, it stayed in the bank. Right? So it stayed in the bank for 2 years. And so I can treat it like it's own little separate mini account. I already know how to do that because remember, this is going into a compound interest account, 4% APR compounded annually. I already know how to do that. I'm going to do that with my compound interest formulas. That's $1,000 to start, staying in the bank for 2 years. Remember, at the end of year 1, it didn't grow during year 1. So it stayed in the bank for 2 years, growing at 4% APR, compounding annually. So that is $1,000 growing at 4%, 0.04. That does not need to be split up because I'm compounding annually. I'm not subdividing my years here. So this 0.04 does not need to become a fraction like it usually does. And it's staying in the bank for 2 years. That looks like something I can ask Desmos Calculator to help me do. So let me pull up my Desmos Calculator. 1,000 times 1 plus 0.04. Forgot my parentheses. Raised to the second power. And there we go. And we're lucky that the decimals didn't get so long that we had to round this off. That is $1,081.60. Right? We can always keep adding zeros at the end if we need to. $1,081.60. $1,081.60. Remind myself that's the basis. So let's do the same thing again, right? But now for the second payment. How long did the second payment stay in the bank? Remember, it only got deposited at the end of year 2. It wasn't there at all for year 1. Nothing happens there because it wasn't even in the bank yet. Nothing happened during year 2 either. Only at the end of year 2 did it go into the bank, and it stayed there for all of year 3. So it grew in the bank for 1 year total. Well, let me take this over and do this calculation much the same as I did the other one. Matter of fact, it looks almost exactly the same. It's still 4% interest. It still does not need to be subdivided, but now it's just the first power. And when I go to Desmos Calculator to help me do it, I can actually just change that exponent. Let me go back, delete it, first power. Nothing changed except the power. And there you go, right? Even easier. $1,040 exactly. There we go. So again, it's like every payment into this annuity account is like a separate bank account. I'm certainly treating it like a separate bank account because I do not want to deal with, 1 month of interest on interest here and 2 months of interest on interest there. Like keeping track of all of that separately would be a gigantic pain in the butt. Right? Because I'd have to keep track of how many times each interest payment has been in there and what's coming in. Forget it. I'm going to treat every payment like it's its own separate account. At the very end, I'm going to add them all together. How about that third payment? That third payment only got deposited at the end of year 3, right? It wasn't in the bank account here or here. And it only got deposited at the end of the 3rd year. So there's no time for it to grow at all. So this one had no growth. Its value at the end of year 3 is still exactly $1,000. It did not grow at all. Right, so let's see. I should be able to add these things without a calculator. That's $3,000. Of course, that's the basis. And then 8160 plus $40, that's $3,121.60. I don't know why I put another comma there. $3,121.60. That is the total future value for this entire annuity at the end of year 3. I don't know why I magically unerased that all of a sudden. That's my total future value for this annuity. Now I know what you're thinking, Professor, my annuities might get really long, right? If I were doing this for a house payment, a mortgage, don't we usually pay on houses every single month for 30 years? Well, yeah, that's 12 months times 30 years. You're not telling me I'm going to have to do this table for 360 payments, are you? That's a lot. Right? Thankfully, no. Our formula is going to help us here. I'm going to borrow a formula from calculus to help me put this together. Don't worry, we don't actually need to do the calculus. This formula comes from calculus. It's something I would cover in more detail, say, in a Calculus 2 class. But we're going to take the hard work of the calculus people, and we're just going to use their end result. Thankfully, we won't have to do this formula every single time. Here's what the formula looks like. So in my annuities, the total future value is equal to the payment times a number. And that number is going to be a fraction, unfortunately. 1 plus I to the n power minus 1 all over I. I don't know what you're thinking, Professor. That formula looks really big and nasty. How am I supposed to remember that? Right? One, you don't technically have to, right? If you haven't noticed, this class is kind of online. So if you wanted to make a note card before your exam, this might be a good formula to put on that note card. But when I have students in my regular classes, I tell them to remember it this way, right? The future value is a multiple of the payment, right? And that kind of makes sense, right? Because if we scroll back up, the future value was 3 times $1,000. That was the basis anyway, right? That $3,000 that we put into the bank. So if there were no interest, I would assume that this thing in big bracket square parentheses here, right, I would expect all of that to be exactly equal to 3. Right? Payment times 3 equals future value because there was no interest. But that's not how it shook out here. Right? What this big nasty fraction, the 1 plus I to the n power minus 1 all over I, is telling you is, well, you know what? The interest on interest means that I'm earning more than just the total number of payments that I'm putting into the bank. This tells me exactly how to calculate how much more than the total number of payments it is. And this is the part in the square parentheses. This is the part which comes from calculus. And so if you want to ask me during one of the other live sessions to explain where it came from, I'll do my best to explain it without calculus. But for this class, it's not super important, right? Again, because this formula is already made. You're never going to have to remake this formula in this class. We're just going to have to use it. Right? So let's plug the numbers in from our previous example to see if we get the exact same result. Remember, in our previous example, we had $1,000 payment every year for 3 years, and my I was 4% APR, which was not subdivided. I didn't need to make that a fraction. So let's plug those things into my present value formula. My future value formula. We'll do present value in a minute. My future value formula is 1,000 times 1 plus decimal, 4%, to the third power, minus 1, all over I, that decimal, 0.04. Okay. Now, again, we're going to use Desmos Calculator to help us do this, right? If that's freaking you out a little bit, Desmos Calculator can help me do it. So let's clear all this out. 1,000. Desmos Calculator doesn't have square brackets, but that's okay. I'll just put a big fraction inside regular parentheses. 1 plus 0.04, close parentheses, raised to the third power, minus 1. I tap to the bottom. Desmos Calculator has left and right buttons, but if you have a keyboard, you can press the down arrow. But I've got my keyboard folded away. Divided by 0.04. There we go. So thank goodness Desmos Calculator can help us make sense of all of that and make it to where we're not going to make any calculator errors. By the way, if you do this on your test and you want to show your work because you know you need to show your work, right? Just write this. Write down exactly what you would type in Desmos Calculator, and you can even write it there. I typed it into the calculator. That's perfectly valuable. Remember, the calculator work is not really math. I know it feels like math because that's what you spent the first probably 6 years of school doing, was learning how to be a calculator. But now that we're in college, right, the math is actually learning how to solve the problems, not really the calculations anymore. So I'm okay with leaving this to the calculators. That's what they're designed to do. We made calculators for this very reason. Our future value is $3,121.60. And if I remember correctly, that is exactly the number we got up above, $3,121.60. Awesome. It's kind of cool how this formula takes care of all of that entire table in one go. And again, we have calculus to think for the formula. So thank you, calculus. Everyone always asks, when are we ever going to use calculus, Professor? Well, we do. We just don't always actually recreate what they've done. So we can just plug numbers into this formula, right, for the rest of time to work with this. Let's do another scenario. Let's say that I'm saving up $50 a month. Oops, don't need a highlighter. So let me save up $50 a month. And I'm going to leave it in the bank for 10 years. But my bank account earns, let's say, 2% interest, but that's going to be split out per month. Let's double check here. Month, month, not month. Holy crap. Okay. So N needs to be measured in months here. And you're probably already thinking, Professor, I know how to do that. I can turn a number of years into a number of months. So let's do that. Month, month, month. They all have to match. Now that they all match, I can go to the formula. Just like before, the future value, how much be worth at the end of 10 years. I always write the formula. I will always encourage you to write the formula. Even if you have it written down on your note card, I still say write it. You'll find that it'll be easier and easier every single time. Let's plug in some numbers here. Again, they're going to look a little silly because we're going to have a bunch of fractions here. $50 times 1 plus I, 0.02 over 12, raised to the n power, 120 months, minus 1, all over the I fraction. Yeah, that looks silly, doesn't it? Good thing Desmos Calculator is going to be doing this for me. The hard part for me is getting it all typed in. Now, I know what you're thinking, Professor, why can't I just do 0.02 divided by 12 in my calculator and use that decimal? Well, 0.02 divided by 12 is 0.1666. It's repeating, right? It goes on forever. If you round that off, you create an error necessarily, right? Rounding always creates an error. But the problem is that when you raise that error to an exponent, it becomes bigger. And how big is the exponent in this problem? 120? That error would get very, very big, right? Maybe not big enough to matter in this scenario where the payment is only $50. But if I had a larger number, you would be surprised how quickly that error bubbles up to the surface and would actually cause you to get the wrong answer in this case. Right? So I'll always encourage you to type everything in, even the fraction, into Desmos Calculator when you're working these problems. If you want to use the answer key on your keyboard, your calculator keyboard, that could work too. Like if I did 0.02 divided by 12 and it gave me that decimal answer, then I could go to my calculator and do 1 plus answer raised to the 120 minus 1 all over answer. So the answer button will help you there, right? But if we're going straight to Desmos Calculator, I'd just say type it all in Desmos Calculator. It's not going to hurt. I want to see all of that anyway. It will take a little bit longer. Yes. Let's see if we can get this in here. 50 times big parentheses, fraction inside the parentheses, times 1 plus 0.02 divided by 12. Notice how the Desmos automatically makes the 0.02 divided by 12 a fraction. Right arrow, close parentheses, raised to the power of, what was it? 120. Yeah. Up here, please. 120. Right arrow, minus 1 over 0.02 divided by 12. And yeah, that looks a bit silly, right? But it is exactly the same way I wrote it down on my paper. And so Desmos Calculator actually saves me quite a bit of work here by doing all this for me. And since we're talking about money, we'll round our answer to 2 decimal places. $6,635.98. $6,635.98. 663598. Just checking to make sure I copied the correct number. Awesome. Way awesome. Again, props to Desmos Calculator for helping me do this. Right? So at the end of 10 years, here's how much I would have in the bank, paying $50 a month. Right? That's a pretty straightforward calculation. Another calculation that might be asked of you is a follow-on question, which says, well, okay, how much interest did you earn during that time? Remember, interest is usually what I call big I. Big I is the amount of interest. Well, to do that, let me start with the future value. That's how much money I really have at the end. And let me subtract how much money I put into it. How much money did I put into this? That's N times the payment, right? I put in $50 a month times 120 months. So if we start with $6,635.98 minus 120 times $50 a month. Desmos Calculator will do the answer for me. So let me go back to Desmos. I'm going to press minus. Nope. I thought it would do the minus. Desmos Calculator does have an answer button. It's down here. answer. Yeah, it brought the answer. If you want to use the rounded, right, that's fine too. 663598. It's not going to hurt anything to retype that number. Minus 50 times 120. It tells me the extra amount. This is the extra amount more than I put in, which is the interest amount, was 635.98. That's how much extra came from the interest. I put in 120 times 50. And that's $6,000. I think if I've been doing my mental calculations correctly. The extra $635.98 came from interest. Right? So there's not really a formula. I guess you could call this the interest formula for annuities, but it's not really a formula, right? We just took the final value or the future value and subtracted all the stuff we put into it. And so that's why I don't really call it a formula per se. That's just taking what you have and minus what you put into it. That's pretty cool. And so you could talk about the effective interest rate over the entire 10-year period. You could say, well, over 10 years, this is what we call the yield. Over 10 years, I earned this much interest, and I put in this much. That's N times PMT, 120 times 50. Well, let's see what that is. 635.98 divided by 6,000. And that is an interest rate. I'm going to turn that back into a percentage. That's move the decimal place twice. 10, so that's 10%. 0.6. I'll go one decimal place there. So that's 10% over 10 years. So I earned about a 10% yield return on investment over 10 years. And you're thinking, well, that's not that good, because if I divided that out, that would be about 1% per year. And that's what we're getting. And the interesting part about that is that, right, the interest rate, remember, was 2% per year. Right? So why didn't we end up with 20%? That's 2% times 10 years, 20% total. And the reason for that is because, right, I didn't have a lot of money in this bank account when I started. Right? It grows slowly. And yeah, there were jumps because I put extra money in the account. Right? Most of the money didn't come in until later. And so, yeah, that there's not a lot of money. There wasn't a lot of time to grow at 2%, right, for most of that money, right? So that's why the yield, the effective yield, didn't actually turn out to be 20% like I might have expected, 2% times 10 years. So I can calculate how much money it will be worth. Right? I could also take this formula and rearrange it, just like I did the compound interest formulas. Rewrite the equation, the formula. What if I wanted to solve for the PMT? Right, that's something I want to ask myself quite often, because I want to say, I want to save up some money. I want to buy a new car. That new car is going to cost me $30,000. So I know what the future value should be, $30,000. But I don't know the PMT. How much money should I save up every month to get there? Right? Again, this is assuming I'm going to pay for the car outright. This is kind of the opposite of what you would do if you were taking out a loan to buy this car. Right? I'm saving up to buy this car. I want the money in my hand before I go buy it. So let's assume that the future value is known. I need $30,000. And I have a while to get it, right? My bank account, let's say I'm going to invest in a different product. Let's say I'm going to earn a 5% return. And that's going to be every quarter divided by 4 times per year. And let's say that every quarter, that's 4 quarters. Let's give ourselves 5 years to save up, right? 5 years times 4 quarters equals total of 20 quarters. Right? This is a per quarter interest rate. After I divide it by 4, it's a per quarter interest rate. So I need to solve for PMT. And that would be a quarterly payment. Again, I want all of my time units to match quarters, quarters, quarters. I'm not going to go straight to my formula because my formula is not exactly written in a way that I can work with it just yet. I'm solving for the PMT. I don't want to plug in a bunch of numbers there because I'm the algebra guy, remember? I'm going to rearrange the formula before I plug in the numbers. And the cool part about this is that because I'm solving for the PMT, basically I need to move the entire fraction to the other side of this equal sign. Well, let me do a little bit of algebra. And I know it seems weird, but what if I took this entire fraction and I turned it upside down? Do you see how the top part would cancel with the bottom part? The bottom part would cancel with the top part. I'm gonna rewrite this down below. I'll rewrite the same thing, but call that the reciprocal of a fraction. You might have even heard that word before. Now, if I multiply times the reciprocal fraction, it cancels out. Equals PMT times. This is the original fraction, 1 plus I to the n minus 1 all over I. And if I multiply it times the reciprocal fraction, I over 1 plus I to the n minus 1. Do you see how it completely cancels out? The top part cancels out, the bottom part cancels out. And it leaves me PMT on one side of the equation. I flipped it around because I'm looking for PMT equals future value times the reciprocal fraction. So I will never give you this version of the formula on the test, right? Because it comes from the first version, right? All I've done, just like, you remember when we did it with compound interest, we actually used negative exponents? Well, because this fraction is a bit more complicated, I'm not going to try to make this big fraction with a negative exponent. It's already a fraction. Let me just write the reciprocal version of it. And that's what I've done. And compare that to the original. The only difference is the payment and the future value swap places, and we have the reciprocal version of the fraction. Okay? So now we have numbers for all of this stuff. So my future value was 30 years. And my I was 0.05. That's 5%. Divided into 4 quarters per year. And then we will go into 1 plus I, 1.0, 1 plus 0.05 divided by 4. To n, that was 20 total quarters minus 1. That's something Desmos Calculator can help me do. Let's try typing all that in. So that is 30,000 times fraction. I is 0.05 divided by 4. The bottom is 1 plus that same fraction, 1.05 divided by 4. Right arrow, close parentheses. Raised to the 20th power right arrow to get out of the exponent, minus 1. I like closing my parentheses manually. And so there's my payment, $1,329.61 when I round it to 2 decimal places. 132961. And this is a per quarter payment. Remember, the time units must match, and this is a per quarter. And you want to say, Professor, what if I wanted to make that a per month payment? Right? I know my bank account only is going to calculate this per quarter, but I want to put this in my monthly budget. Well, there are 4 months per quarter, so I can divide that number into 4 pieces. That's perfectly fine. After we've done the calculation, the time units no longer have to match. So if I divided this by 4, I could make it a per month payment. You could think about that as me just, I'm going to put money into the bank every month. The bank is only going to calculate every quarter. $342.30 per month. So that's not too bad. And that's actually a pretty decent payment for a card that's going to be $30,000 in 5 years. Right? But then again, right, maybe I don't want to work this way because I'd rather buy the car today. Right? In 5 years, who knows how much cars are going to cost? Maybe the car that I buy for $30,000 today would actually be a decent car. But if I bought a car 5 years from now for $30,000, it might not be nearly as nice of a car. And not to mention, I'm not going to have a car in between now and then, right? I'm going to have to wait until the end to buy that car. We'll talk about the opposite of this, the present value version of the formula, in just a few minutes. But this is the future value, right? Basically, future value is going to be used anytime we're saving, right? Anytime we're making payments now and we're waiting at some point in the future, that's going to be a future value. Right? You can think about that as saving up towards a goal. Maybe I'm saving towards retirement or saving towards paying for college for my kids. Right? But anytime I want to do this the other way around, right? I want the value today and I'm willing to pay it back with payments. That's going to be exactly the opposite. Before I go into that, I'll mention that we can use the present value formula to solve for I. Here's my highlighter. I'll use a red highlighter. I can't solve for this I. You see it occurs in more than one place. I can't really solve for that. It appears both in the base of the 1 plus I and in the fraction. I will never ask you to solve for I, except I will ask you to plug and check, right? I could plug, like if I gave you future value and payment and N, you could plug in a bunch of numbers for I to check. I think there's a homework question that really asks you to plug in numbers for I and check. Start with 1%, then 2%, then 3%, right? Plug in until you find a percent which best matches. Right? But I will never ask you to solve for I. Right? I might ask you to plug and check for I, but you can't solve for I in this class. I could ask you to solve for N. You remember when we did N for the compound interest formulas? We needed to do algebra, and it ended up being a logarithm thing. Right? It will be the same thing here. Right? I think there's a video posted on one of the homework problems that shows you how to do that more specifically. Of course, I'll help you do it too. Right? I'm going to move on though. Right? We don't do N that often, but do look up how to do it. Right? It's not something which is impossible to ask. It's just not super common. Let's talk about the other version of this. That would be called the present value version of the formula. Right? Now, if we use the present value version of the formula, I can say, you know what? I'm willing to make a bunch of payments in the future, or I know some payments in the future are coming in, right? But I want to know what the equivalent value is today. You can think about that is if I had the present value today, I could just go put it in the bank, and it would be the same thing as waiting for all these payments to come in, right? If I put the present value in the bank today, and I put all the payments in the bank today, and as they came in, at the end of all of the payments, I would have the exact same amount. So the present value is the equivalent amount of all of the future payments. Let's do another table. And I'm going to use the same numbers as before, but instead of calculating the future value after 3 years, I'm going to take into account the present value of all of these payments. So just like before, right, I'll give myself a little bit of room here just to remind myself of what the payment schedule was. Go back up here to the top. I'll try not to scroll too fast. I don't want to make anybody sick. The scrolling. On the table, it was $1,000 per year for 3 years, 4% APR compounded annually. Matter of fact, I'm super lazy. I'm just going to copy and paste that down below. Scroll, not too fast. Copy, paste. Thank you. So just like before, remember these monies come at the end of every period. So this is the end of year 1. Sometimes I like to write sort of at the end there to emphasize that's the end of year 1, the end of year 2, and the end of year 3. Now let's see how much money that's worth if we bring it backwards. So how long will this ungrow? Right? Remember, it's at the end of year 1 that we made this payment. So this is actually minus 1 year. To bring it back to today, it's minus 1 year. Okay? And again, remember, when we did the solving for P part in the compound interest formula, we had negative N as part of that. So I'm actually not too sad to write negative 1 year because I'm thinking about it as, you know what, I'm growing it backwards. Here I'm growing this one backwards for 2 years. And here I'm growing this one backwards for 3 years. So let me calculate the equivalent of all of these payments. I'm going to have to do them separately, just like I did in the upper table. So the present value is equal to, you know what, let me write the original formula. A is equal to P times 1 plus I to the n power. But we're not solving for A here, we're solving for P. P is equal to A times 1 plus I to the negative n power. I remember that's me dividing by that big set of parentheses, but rather than showing a fraction, I'm going to bring it up to the top of that fraction with a negative exponent. So let's calculate. I've got 3 different ones to calculate with. So the first one is 1,000. 1 plus my I was 4%, 0.04, not subdivided, with 1 year backwards, minus 1. Well, let's ask Decimal's calculator what that is. 1,000. Excuse me. 1,000. I'll get it right one time. %4 to the negative 1 power. So that's 961 and 54 cents. Another way you can think about it is, if I put $961.04 into the bank today, it would be worth $1,000 at the end of year one. So that's the equivalent present value of that one payment. If I did it for the second payment is $1,000 sitting in the same bank account, so the same I, but now that's 2 years. And luckily, I can change this in my Desmos calculator as long as I don't press enter. But even if you do press enter, you can actually go back up here and change it. That's the cool part about Desmos calculator. 2 years, $924.56, 92456. And you can think about that as, if I put $924.50 in the bank today, it would be worth $1,000 at the end of year two. Right? So I'm breaking this into sort of sub accounts the same way I did for future value. But these amounts are going down because I'm bringing them back to the present. Right? I'm ungrowing them. I do the same for the third payment, but it's going to be in the bank for 3 years. So luckily, I can just go back and change this again. I'm going to tap up here to come back up here, right arrow. There we go. Change that to -3. 888.90. Oh, I'll just make that 889 even. 889 even. And if I put $889 in the bank today, it would be worth $1,000 at the end of year three. So do you see how if I put all three of these present values in the bank today, they would be worth the equivalent amounts as we came to them in the future? What is the total of all of that? I'm going to need my calculator to do that. So 961.04. Unlike the last one, I'm not going to try to add those three numbers in my head. 924.56. Of course, I can't type. And 889 even. The total present value is $2,774.60. Remember, I always go to 2 decimal places. So that's the total present value. If I had that much money in the bank today, it would be worth the same amount as all three of those payments coming in, right? So you can think about that as sort of cashing out all the payments before they ever happen, right? You would be equally, right? You wouldn't care about having the present value today or waiting for the payments to come in. Of course, we know that's not really true, right? Because money today is better than waiting for money in the future. It's just that what we've done is we've mathematically accounted for the amount of growth that could happen over 3 years, right? In reality, if I went to say JG Wentworth, right, 877 cash now, they wouldn't offer me that much. And even if that was really the interest rate they could earn, right? Because they know and we know that money today is worth more than money in the future. And that's their whole business model. Right? So they would offer less than this, right? One, because that's how they make their profit, by offering less than that. And two, because they know that money now is worth more than money in the future. I'll finish my table here, $889 even. We call that the present value. And the neat part about all this is that basically present value and future value work together, right, is a way to sort of scrub through this. When I say scrub through this, I'm thinking, of course, of, think of like a timeline, right, or like a video. If I were playing this through like a video, right, if I put $961.04, that's the present value for year one, and I played the video, it would be worth exactly the same when I got here. And if they're exactly the same when I get here, then they would be exactly the same every time after that. If I put $924.56 in the bank now, right, it would grow and it would grow and it would grow. But when I got to the end of year two, it would be exactly $1,000. And then every time after that, it would be the same because they matched up at the end of year two. If I put $889 in the bank, it would grow and it would grow and it would grow. Right? But at the end of year three, it would be exactly $1,000. And every time after that, it would match up. And so the cool part about that is that if we let all of that stuff grow all the way till the end, I should get the future value. Okay? Want to see something really kind of cool? Let me treat this like a bank account which doesn't have any interest rate, anything on it at all. I mean, it will have the interest rate, but it won't have payments on it. If I take the present value and I let it grow for 3 years, I should get the future value. Because remember, once they match up, they should grow at the same rate. And wasn't the future value the growth of all of that stuff at the end of 3 years? Let me plug this into my calculator. 277460. 1 plus 0.04 doesn't need to be subdivided. 3 years. $2,774.60. 1 plus 0.04 raised to the, I'm going to go outside the parentheses, raised to the third power. 312105. Hopefully, there might be some rounding errors that happen there. Let's see, 312105. Was that the future value? I'm going to go all the way back up here to the future value. 312160. It was very close, right? The reason those two don't match up exactly is because of the rounding errors, right? Especially when you do your present value, you're subdividing. See how all these are? This is where I calculated my present value. So we did -3 power, -2 power, -1 power. Do you see how we had to round off all of that stuff? Every time we rounded off, we made an error. And so those errors add up. And so if we were doing this truly correctly, I would have to make a table for you, right, which took into account all of those pennies that get rounded off every month. We're going to do that next week. That's called an amortization table, right? But my generic formula, it's a pretty good starting place, and it gets me really close to the final value, the correct answer. Right? So we didn't get exactly the same, but we got really dang close to it. Right? And you can think of that as if I had the present value today, right, that would be the same as me just putting that in the bank and letting it grow. And at the end, I should get exactly the same future value that I calculated up above. And basically, present value and future value are a way to turn this big nasty sequence of payments, right, that we were scrubbing through, turn that big nasty sequence of payments into a flat dollar amount. So I don't have to worry about, oh, where am I in the middle of this process, keeping track of all of these payments. I say, screw all that. The present value is at the beginning. The future value is at the end. I don't want to talk about any of this middle stuff. Outside of where the payments are happening, it grows just like compound interest. And that's exactly what present value, future value are doing. So that's neat. Right? Again, I don't want to have to do this with a table every time. So there better be a formula to help me. And there is, thankfully. The present value version of the formula is this, PMT times another big fraction. But now it's going to look like this, 1 minus 1 plus I to the negative n over I. Hey, that looks pretty close to the future value formula. Here's the difference, right? Instead of parentheses to the n power minus 1, oh, sorry, not n, negative n. Now I'm doing 1 minus parentheses to the negative n power. And the way I think about it is this, right? This set of parentheses to the negative n power, right? That's a number smaller than 1. So that's why it has to be 1 minus parentheses, because it's 1 minus something smaller than 1. If I did it the other way around, parentheses to the negative n power minus 1, it would give me a negative number. That's not what I'm looking for. Okay? Compare that to the future value formula. Here's the two formulas side by side. And parentheses to the positive n power is a number bigger than 1, which explains why it had to be parentheses minus 1 in the future value formula, because otherwise it would give me a negative number. I don't want that. So they have to work this way. And in both of them, you can see the 1 plus I interest happening. The 1 plus I looks very much like the compound interest formula. Right? It is the compound interest formula. Right? But the whole shenanigans, big fraction around it, that came from calculus. Right? That let me see exactly what I was doing here. So seeing both of these formulas is actually really nice. And just like in the future value formula, I could calculate the payment for you by using the reciprocal fraction. Right? I could multiply times the upside down reciprocal fraction, calculate the payment from the present value by using the reciprocal fraction. Remember, that's the same fraction, but upside down for the same reasons, right? It would cancel out for the exact same reason. I could calculate the payment from the present value. And yeah, I could calculate the n as well. And I think one of the homework examples is calculating the n using a logarithm. I think there's a video posted there. If not, I'll come back and amend this. But the main one is the present value and payment. We see the present value formula a lot, especially when we're talking about loan scenarios, right? Because when I buy a car, when I buy a house from the bank is paying them a day. That's the present value. You can think about that as how much you're borrowing. And you are paying the bank back with a series of payments. That's PMT. Right? And so if I knew how much money I was buying a car for today, I could calculate the loan payment, the PMT, right, using this formula. And if I knew, right, how many times I was going to draw out of my retirement accounts, I could go back and calculate how much money I needed today to fund that. That's the present value. We do this a lot in lending scenarios. So let me do the exact same lending problem with a car from before. Remember that the car before was a $30,000 car. We paid for it in 5 years with, I think, 2% interest. Let me go back up and see. Yeah, per quarter. Right? Now, I don't know too many car loans which would do this per quarter. Right? I'm going to do it per quarter only because I did it before per quarter. I want to compare, right? Because the payment that I get is not going to be the same. Right? So normally this would be like a monthly thing because you make a car payment every month, right? But we're going to do 5% APR per quarter for 5 years, only because I want to compare this formula with the one we're about to do. I want to make the match. I probably should have done this per month before, but I'm not going to go back and fix that. So let's buy the car today. That's the present value for $30,000. And let's pay it back at 5% interest per quarter. That's why it's over 4. And 5 years. And that's 20 total quarters. I'm going to break out my PMT formula. I know I just wrote it down. You know what? I just wrote it down. I'm going to plug in the numbers. You see the formula there. $30,000 present value times 5% divided by 4 over 1 minus 1 plus 5% divided by 4 to the negative 20. Again, it looks really nasty. It's something I'm going to ask Desmos calculator to do for me. Desmos calculator. Yes, you. 30,000 times fraction 0.05 divided by 4 divided by 1 minus 0.05 divided by 4 raised to the negative 20 power I'm going to close my parentheses manually just because I like it. Uh-oh. Did I do that wrong? I probably did. Oh, I forgot my 1 plus in here. I panicked for a minute. I panicked. I forgot my 1 plus in that set of parentheses. You can see that the numbers get really wild if you miss it up because, again, that's a really big exponent. So if you make an error, especially in the parentheses, that makes a really big error in your final answer. All right, so I fixed it. Thank goodness. Woo. And it tells me that the payment for this loan would be $1,704.61. 170461. And that's a per quarter payment. And we know that, again, that's not super realistic. And we divide that by 4 months per quarter, 170431, divided by, oh, I'm going to use my answer button here, answer, divided by 4. That's $426.15. 42615 per month. So let's compare that to the monthly payment that I had up above. Remember, up above, we'd use the future value formula because I was saving up to buy the car in the future. 42615. Ah, there we go. Here we see the difference. See, $342 is all I needed to save every month to buy that $30,000 car in the future. But if I bought the car today, I'd have to pay a larger amount per month. Right? And again, there's a few reasons for that, right? Certainly the difference being I have the car today, right? But when it comes to future value versus present value, when I'm saving up, the balance starts small and gets bigger. And when I'm saving up, the balance starts small and gets bigger. That's the shape that I expect. That's the future value. So most of the interest that I earn doesn't come until late in the process. It doesn't have enough time to grow that money. But when I'm borrowing money from the bank, the balance starts high and it pays back down to zero. So when I borrow from the bank, all of that money is in my loan earning interest for the bank. I'm paying interest on the full amount, right? For a lot right at the beginning. So the total amount of interest would be more in the present value loan situation than for the future value saving situation. And that's assuming that's exactly the same interest rate in both directions, right? It's really interesting. This is, by the way, why the bank doesn't care if you refinance your car or refinance your house, right? You see how most of this interest, when the balance is high, that's where the interest is high. When you borrow things, most of that interest comes in right away and it goes down over time. So if you want to refinance your mortgage, the bank doesn't care. The bank earns most of its interest that will ever earn in the first 2 or 3 years. And I think it earns like 2/3 of the interest that the bank will ever earn on your house in the first 5 years. And so the bank doesn't care if you refinance. As a matter of fact, sure, it's earned all of its interest. It's happy to have the rest of that money back right away because now it's fully paid off. You're some other bank's problem now. Same thing with cars, right? The bank has earned interest in that very beginning. So they're not sad to have you refinance to go somewhere else. Anyway, so that's the difference between present value and future value. I always think about it like this. If you're saving up, usually you're making the payments now and you're calculating the value at some point in the future. That's a future value thing. If you're buying something now, and that's usually a borrowing situation, and you want the value now, and you're making the equivalent for a future stream of payments, that's a present value thing, right? That doesn't mean that you can't do both at the same time, right? You'll see scenarios where both happen at the same time. Most of the time, this is the retirement scenario. When you save for retirement, you usually say, hey, I know how much money I want to pay out to myself every month. I know that, right? And so I'm going to live for a certain amount of time, and when the balance is zero, I guess that's how long I expect to live, right? So you would do your calculations, and you would find this present value, right? That's how much money you need in the bank the day you retire to pay yourself that PMT every month. You would then turn around, make that a future value. You say, you know what? I need to have that money in the bank at some point in the future. And I know how long I've got to do it. So now I can calculate how much money I need to put into the bank now to save up for that future value, right? The present value and the future value. There we go. Sorry, my internet cut out for a moment there. I don't know how much of it got cut out, so I'm gonna restart my explanation. Right? The retirement problem is you're paying yourself a certain amount of money, the PMT, and you're drawing out from it until it's exhausted. Hopefully it lasts until right as long as you plan to live after you retire, right? Because once it gets to zero, it's gone. Okay? You would plug that into your present value formula and figure out how much money you need in the bank to pay yourself that PMT. That's your nest egg, how much you need in the bank the day you retire. On the flip side of that, that's the future value. When you're working right now, that's how much money you need in the bank the day you retire. And so you calculate backwards and you say, well, how much do I need to put in the bank now to be worth that amount in the future? I'm saving up to that. It's two halves of the same problem. You would actually do both of them to figure out how much money you need in the bank to pay yourself a certain amount in the future to get down to zero, because of course you start with zero and you're saving up to the nest egg. And then on the other side, you start with the nest egg and you draw out back towards 0. So these two formulas work together, right? Because not every problem is always a pure savings or pure borrowing situation, right? Sometimes we need to do both. Sorry about the internet hiccup that happened there. Hopefully it didn't cut off too much of my explanation there at the end. I just looked up in the middle and saw, oh, hey, you're not connected anymore. Oops. I'm available with questions, of course, and I will see you guys next week. Have a good one.